Audio check, audio check.
Check, 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 check. Mic test, testing. Microphone test. Check, 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 check. Check, check. 1, 2.
Can everyone go ahead and grab a seat? What? Where's, do we have WebEx on? It's on? Okay. Okay, that was way too well behaved for this crowd. Anticipation. Just wait a minute for a few extra people to come in. All right. Good morning, everybody. Good morning. See, now you're getting the hang of it. It shut off, that's what I thought. Pause.
Do you want to be sharing your screen or not?
Oh, yeah, that's fine.
Okay.
Thank you. For sure. To hide the magic command. Command option shift. Take two. So good morning, everyone. For those of you who don't know me, I'm Peter Fox. I'm the outgoing president of the ESIP Federation. And the purpose here is just to give you a little introduction and welcome to the winter meeting. And I usually do that by sort of saying, The printed material that we have at the desk, I know it's common for people to come to a meeting and not pick up the printed material anymore, but there's actually a lot of really good and useful information. So even if you pick it up and put it back, I highly encourage you to do that. In particular, the frontiers in earth sciences, big data is the theme of this meeting, and I'll say a little bit about that as we go along, why we have a theme and so on. And the program, please take a close look at the program. I'm going to start off just by giving you a few logistical things, and that is on the printed programs, unfortunately Amy Luers from the Office of Science and Technology Policy is unable to join us due to not getting clearance to speak. So we will have 2 talks in the late morning session, and we'll adjust accordingly. And the next thing is that somewhere in the program, it was indicated that the awards would be tomorrow. But as you see on the printed program, the awards are at lunchtime today. That's the Martha Maiden Award, and President's Award, and Catalyst Award, and so on. So please come along to that. It's an important part of ESIP. And so I think in terms of logistics, that's it. So welcome. For those of you who are in ESIP 101 this morning, you've seen the slide before. Many of you have seen it before. It's a graphic representation of people assembled in this room, coming from multiple different stakeholder areas, and really it's the mixing of you people all in plenary sessions and in working sessions that are going to occur over the next 2.5 days around topics in data and information. And that's really what ESIP is about. At this point, we get to do what we call ESIP calisthenics. Those old timers will know what that is. So this year at ESIP 101 this morning, we had an introduction for new members and new attendees. So if you are either a first-time attendee at ESIP or a new member of ESIP, please stand up. All right, so that is excellent. Remain standing. So remain standing. The first thing you have to realize is, as president, I have great authority here. So outside on the table, and Emily, I'll introduce in a minute, has some of these. There's a green badge that says first timer. That means you as an individual are at your first ESIP meeting. And since I've been in America a long time, let me reassure you there's no hazing ritual involved. We do make a little bit of fun of you, but it's also to offer advice, assistance, guidance if you need it. Now, that is distinct from the yellow tag, which is the new member tag, which is really associated with your organization that may have just joined or is already a member of ESIP. And so you as an individual and you as an organization or a project or whatever really are welcome at this meeting. So put these on. The other one, okay, guys can sit now. Thank you. Is the I tweet tag. So outside there's a monitor that's got a rolling collection of the Twitter stream. We're not fanatical, we never trend or anything like that, but it is a useful way to find out what people think is going on in the plenaries, things of significance, but it's also a really useful way to see what's going on in breakout sessions that you're not in, if there's something really interesting that you might want to change rooms for. So just keep that in mind. I also use this opportunity, since it's the end of the year, to acknowledge the leadership of ESIP. Most of you are sort of pretty much unaware of the elected leadership and what we do, but this motley group here has been together for almost a couple of years now. So we have Emily Law. Could all the leadership people who are here please stand up? Christine, Justin, Luann, Ted, Ethan, Ken, Tyler, and Danny in the back. So do we have everyone, do we? Where's Steve? Oh, Steve, right there, yeah, Steve. So we have everyone here. And Bill, I forgot to mention Bill. So these are the people who mostly are all elected leadership. They're chairs of committees or other elected officials. And Denise, where's Denise? Denise Hills is one of our ad hoc committee chairs on the nominations committees. So I refer to her as the arm twister extraordinaire. So I just want to thank these people. You'll see that tomorrow morning on the agenda there is an ESIP assembly where the membership, i.e. people who represent the organizations, come and we have our business meeting, and we'll be sort of ratifying the elections for this year and conducting other business such as accepting the strategic plan and voting on committee requests and so on. If you're new, and I know you usually like to just sort of avoid business meetings, but it's an interesting way to see how the sausage is made tomorrow morning. So please come along. If you're not sure, ask one of us, one of this leadership. And it does not go without saying that the staff, and sort of staff is sort of a too simplified a word for the people who really make ESIP run and happen. Most of you have met or know these people. So we've got Rebecca here. Please stand up, Rebecca. We've got Annie. Erin left the room, of course. And then we've got Dan and Annie Keys outside, and Dan's at the back there. And so I always say thank you just at the beginning of the meeting because, you know, I know what's gone into putting this particular meeting on. So thank you. And yes. All right, so what's my point? So a lot's been happening even in the last 2 years in the data world, and I decided not to go full force with the logos because you know what happens when you put too many logos on a slide? You get sued by NASCAR. And, you know, in NASCAR, I say this sort of partly tongue-in-cheek, that's sponsorship. These are organizations that are somewhat representative or observing programs on the international scene. So the World Data System, CODATA, Research Data Alliance, and the Group on Earth Observations, in which ESIP has a very strong set of collaborative connections. And then on the right-hand side are professional societies, just a sampling of them, that also ESIP is associated with. And sort of an interesting thing has happened in the last couple of years, and that is ESIP as a community, not just the leadership or not just the staff, are being invited into meetings and organizations and rooms because the value of ESIP has become very apparent to these organizations. So there's a fantastic partnership with the American Geophysical Union, which I think we'll hear maybe a little bit more about at this meeting. There's great connections with the other professional societies. And so there are opportunities here for ESIP members and people who show up at ESIP meetings to get exposure to this greater world of data and information and services, and you know, carry their expertise and strike up new collaborations. And so this is something that exists beyond coming to the biannual meetings, the summer and the winter meeting, and participating in the monthly teleconference calls and other types of activities. And so this is my point: is there's even more opportunities for you, both individually, organizationally, and even at a project level, to take advantage of ESIP status with many of these organizations. So if you have an interest in that, professionally or internationally, please come and talk to one of the leadership group or the staff. And this is all a bit of a build-up to the following, and that is in September of this coming year, there's going to be the first ever International Data Week. And it's the origin of a number of organizations, a couple that were on the previous slide. So the International Council for Sciences Committee on Data for Science and Technology, CODATA, the Research Data Alliance, and the International Council for Science's World Data System, meet and come together regularly, and they're all going to sort of meet in a week in Denver. And so it's sort of a unique opportunity, because it's in the US especially, to see really what is happening on the international scene, because, you know, I don't know how many of you get out of the country, but there is a lot of interesting things going on, and also to see, in some ways, how far ahead ESIP is in many, many areas, and how ESIP is influencing these organizations. So my question to you is, what will ESIP do for this International Data Week? ESIP is you. And so I'm looking for ideas. So in the new leadership, I hopefully is looking for ideas of what an ESIP activity might look like at this International Data Week. And we have very good, as I said, we have strong collaborative connections with these international organizations. And we're being welcomed into that particular activity. So just keep that with you. And finally, welcome. We seem to be using this picture a lot. Here's a picture at Asilomar from the summer meeting. These are our Funding Friday, happy smiling faces. I put them up because they, in some sense, represent some of the next generation of people who are stimulating new ideas inside the ESIP community. And if you're at ESIP 101, you'll know a little bit more about Funding Friday. If you want to hear about it at the summer meeting, come and talk to, again, one of the leadership or the staff. And finally, by sort of wrapping up my welcome, I just want to say, please use Twitter. The hashtag is down the bottom there. I don't know at what point we'll say more about the data blog, Rebecca. I don't know when we'll do that, but maybe it's Data Federation or something like that. There's one of the other collaborations with AGU is a new data blog. So ask about that. Please use caffeine carefully, because the sort of the number one feedback we always get from this meeting is that it's very much about networking, right? It's about coming and contributing and listening, but it's very much about making those collaborative connections. So please do that. And for those of you who are at the summer meeting, you'll know that we have a new ESIP type. It's called AB positive, and it will happen. Anyone remember what that is? John, you want to tell them? Okay. Come tonight to the poster session to find out what AB positive is. And I think that's all I needed to say. So get some ribbons on your badges. And please enjoy the meeting. And I'm going to kick off the morning plenary now. So that's right. Good reminder. So especially if you're new to ESIP, there's one thing I think that's really important is we pick a theme for a meeting, and the theme of this meeting is Frontiers in Earth Sciences Data, Big Data. And it's sort of used as an undercurrent for the meeting. It guides the choice of speakers for the plenary session. The plenaries, we don't have extensive plenaries. We have this morning, and we have a little bit late tomorrow morning, partly because of the way the business meeting works. They're really meant to sort of get you thinking and stimulate you, and then you go off into your technical sessions and do your work. So as you're listening to the talks and thinking about the themes, think about how that carries into your technical sessions. That's the reason for it. So. So I'm going to introduce the first speaker, because she's my buddy. And we're very lucky to have Dr. Kerstin Lehnert from Lamont-Doherty Earth Observatory and IEDA to speak with us this morning. And as she's known to do, she will remind us that you should not forget your family in this big family of big data. And so, Kerstin, come on up.
The people are talking here.
Yeah. So that works? No.
Beautiful.
Okay, so welcome everybody. It's quite an honor to be the first speaker here at the plenary, and I was a little surprised actually in being this speaker because, as you can see from the title slide, I'm not really a big data person. I come from the opposite end of the world in working with what we usually call small data. But this is actually an interesting insight from going on the web and searching that there is quite a fuss about small data at the moment and its potential in businesses. And I think that for research, we actually have that same potential. So my talk wants to show you that there are ways to unleash the big in small data. And it's very non-technical, this talk, so it's probably a good start to wake up in the morning and get ready for the rest of the meeting. So we know the earth sciences has really a lot of small data. We have many communities that gather, individual where there are individual investigators going into the field, in the lab, in the experiments that they're doing, gathering spreadsheet level data that are in the kilobytes or maybe megabytes and so on. And while these data volumes are small when viewed individually, in total, they represent a very significant portion of the country's scientific output, as Brian Haydorn stated very correctly many years ago, actually, already by now. And it is very clear that there is a lot of potential in these data. When you put them together, when you actually have them in a way that you can mine that data, it is a breeding ground for new ideas, as he stated. This has been a key sentence for me in the way he expressed it. And ultimately, the small data are small pieces in a puzzle that, when you put it together, build a picture. We study little pieces regionally, temporally in our activities. Many of the awards, small awards given by the funders, get that little piece of the puzzle. But when you put it together, it's a picture that you can, where you find patterns, where you find trends, and so on. And that's why we have to work on unleashing the big in the small data. And so just to start off, I wanted to give you two examples of small data that I'm particularly in my data facility I'm working with. And it's very interesting when you look at how these data are generated, how much effort and how many resources really go into generating these small bits of data. So the first example here is a study of New Zealand dust and how it influenced climate, especially the last ice age. And dust in the atmosphere, understanding where it comes from and so on, helps researchers to understand the entire climate system and its evolution. So this is a study conducted by mostly scientists from Lamont-Doherty Earth Observatory, and the main researcher was a postdoc, Bev Kaufman. And in order to do this study, she actually traveled to New Zealand, collecting it's actually glacial sediments, loess samples in New Zealand, and she actually went to Antarctica and gathered ice that had dust layers. So you can already see what the investment is. All this research, these travels had to be funded, had to be prepared, and so on. So a lot of effort. Example two, it's an expedition that just happened this summer. My husband was on it, that's why I'm easily demonstrating it. Funded by the National Science Foundation, an expedition to the Aleutian Islands to study plutonic and volcanic rocks up in the islands in order to understand the convergent margins and how they contribute to the creation of continental crust. Again, big effort. It was 4 scientists from 3 different institutions traveling to Alaska, staying there for 5 weeks on remote islands, a lot of logistics preparations. Hiring a boat and a helicopter for 5 weeks is quite a bit of money. And what's coming out of this is, I mean, they collected more than 250 samples, so that's already something. But when you look at the number of data points that they want to generate, that's, just a spreadsheet of data. And it's a huge amount of money and effort that has gone into that. But when you come back from the field, it's actually, sample preparation, chemistry, and huge and expensive instrumentation that generates these data that needs to be operated, configured, maintained, and so on. So this is actually the data. This is data for that New Zealand study. You see the few yellow dots on this diagram. That's what the effort was for. And this is how the data is shared then. It's integrated into a publication. It's a data table. And as long as this is the only way we can access the data will stay small. So now let's just take a different sort of step off that track of the small data and actually define what is big. We usually talk about big data with respect to volume, velocity, variety. I mean, you all have heard about that, and maybe you hear about it more over the next couple of days in these big data talks. And there are also other definitions in the meantime, virality and viscosity, interesting aspects that I don't even want to get into. But for me, there is a 6V, and that is what counts to me, and that's the value of data. The data can be big if they are valuable for the research we're doing or for the businesses we are running. So how do we add value to the small data? What do we need to do? So in my view, there is a stepwise process to grow small data into big. First of all, we need to make them findable. That means there is identification, persistent access to it. They need to be accessible. They need to be reusable by providing enough context and provenance information to the data. And ultimately, they need to be integrated, harmonized, interoperable. So that's where I think you end up with big data. And this is the process of adding value to the data. These first two steps in making data findable and accessible is something that many repositories, be they institutional, be they these generic repositories like Figshare or Dryad to a certain point, it has a domain-specific focus. They can provide that. There are data curation standards for long-term archiving, identification, and so on that need to be followed. But that, to me, makes the data not yet really valuable. It's providing the context, providing the provenance information, a certain level of harmonizing, making them integratable is what counts. And I think this is something that needs domain-specific expertise to achieve. Now, there are community data collections. These are small databases which often do this, wonderful databases that many communities operate. But they, on the other hand, are missing the data curation standards of making data persistent, identifiable, and so on. Combining these two levels of contribution or value-added contribution is, in my view, are the domain repositories that can do that. Domain repositories interact with their science community with a lot of disciplinary specific expertise, providing or helping to develop standards, implementing these standards, developing softwares to support workflow, and so on. While on the other hand, these data facilities interact with the publishers. They do data curation activities. They interact with archives and libraries, and with the computer science world, and in trying to stay on top of technology developments and so on. And I've been thinking it really, in some way, matches the image that data science in general has, that we have these different fields of expertise that need to come together. And I don't know if any one of you attended the session on data scientists at the AGU meeting just a few weeks ago. This these three circles were in nearly every talk as being, the critical aspect of data science and having these different legs. So now I'm coming to the data facility that I'm actually directing. And that is, to me, a domain repository that provides this range of services that is necessary to grow data. We do data publication and preservation services. We provide discovery and access tools, but then we also generate data products that have that aspect of reusability and integration that is needed to mine data. And I will show you an example in a minute. And so just by the volume of small data that we have amassed over the years, we have grown the small data to quite some size, I think. Important, the number of individual files that we're making available, but there are also these syntheses that now have thousands and thousands of data sets fully integrated and mineable available to the community. And so, just to show the process here, this is just one of the data systems, or a suite of data systems that IEDA operates focused on geochemistry. We have other disciplines covered in the systems as well. So here for geochemical data, we start off with the data repository, the EarthChem library, that provides ways for investigators to submit their data, to get DOIs, to ensure persistent access through collaboration with long-term archives and so on. But then the data actually is transferred into data syntheses, which are relational databases. And the transfer is actually done by data managers through Excel spreadsheets that are read into these databases and heavily quality controlled. And then we run another portal where we're integrating our syntheses with other syntheses available in the community. This first step, the repository, the EarthChem library, makes the data findable and accessible. The second step, the synthesis, makes the data reusable and interoperable. Just to show, this is an image for one record in the EarthChem library. So the data has a DOI, it links to publications, it links to funding sources. And this is an example how we interact, how the data then links up with the literature. I think this is, it's an important step for us to take in order to really grow the accessibility of the data. But then the syntheses, I just wanted to show you briefly how these work. So the PetDB synthesis is a compilation of geochemical data for igneous rocks, focused on ocean floor samples, and now combines data for about 80,000 samples. More than 2,000 studies that have actually been compiled into this database. The concept is that each individual value in a former data set can be accessed by itself, but it's linked to all the provenance information and all the context that is necessary for somebody to use to actually find data of interest to their study, filter it out, and basically retrieve a new data set that just contains data for their particular interest. So the data output is formatted in a way that people can immediately start analyzing the data in whichever software they want to do that. Let me just briefly show you, this is a start page where selection was made with geospatial information. Here, samples from the Beckart Basin Mariana Trough were selected, and specific rock types like basalts and other igneous volcanic rocks. 2,000 samples were selected that way. This page in the system shows which chemical items are available for these particular samples, and people can make the user can make the selection which of these specific parameters they are interested in. In this case, it was magnesium and sodium and all the rare earth elements. And they can even further say, I only want rare earth elements that were acquired by a certain technique that has the right quality level of what I want. For what I want. And this is the data table they get back and that they can download. They can check more information on methods, on standard measurements, on data quality, and so on. Or they can check what other data are available for a particular sample published over the entire time that is covered in this database, so about 50 years. This is an example for a data set that was generated. This was within 2 minutes. An investigator could go in, look for strontium isotope data across all the literature that has been published in the last 50 years, basically, and retrieve a data set that can be immediately visualized. What it shows here is the individual data points are colored. The color is scaled to the strontium isotope ratio level, and so it shows here that the data points in the Indian Ocean have a higher strontium isotope ratio than the data points in the Pacific and the Atlantic. So that's a real data mining exercise that shows the power of these databases. The value, I think, is immediately visible in the fact that we have a lot of use of this database. Over the last 15 years, we have over 600 citations, which include many highly relevant and highly cited papers with new discoveries and insights that were only possible because of this compilation that nobody else could do by themselves, that had to be maintained by a facility. But you know, we want this approach clearly to work across the entire geosciences. We want the data from other small data communities to be available in a similar way. And that makes it a problem of scalability in the current approach. We, as the IEDA data facility, deal with an increasing diversity of data, and so we're challenged in some way both with the problem that there aren't any data standards for those communities yet. So our data quality or metadata quality control hits the wall and saying, what do you really need when I get a new data type, be it XRD data or other new methodologies? I need to say, what you as a community, what do you decide is relevant for documenting these data? And then our data schemas are not necessarily scalable to accommodate any completely new data types, methodologies, and so on. We have increasing volumes of data, and clearly the efficiency of a quality control process that's done manually by data managers is not necessarily scalable. So that's another problem, and we need tools for and ways for investigators to provide us with better data sets that don't need as much review from our side, and we need to automate the processes more. So how can we grow? And these, I just wanted to give you 3 examples, I think, of activities, of projects that are going on that I think are ways to move forward. And they all have to do with partnerships, alliances, collaborations. And this slide just reminds me that I was recently at a workshop that the National Science Foundation organized. It was cyber infrastructure for large facilities. And multiple times people were saying, well, collaboration, we only collaborate if we're desperate. And I went up at the end with a slide and I said, I am not desperate and I do collaborate. I think we need to, we really need to be behind the idea that collaboration brings a lot of benefits and that there is no other way for us to move forward. So first example is COPDESS, and I hope that many of you have heard about it. Who has not heard about COPDESS? Oh, wow. We should have had a bit more information about it. But okay, this is a coalition of publishers and data facilities to enhance the process of getting data that is part of publications into the repositories and manage them properly. The big advantage of this, or the big impact, I think, of this coalition is that there is consistency of data policy, or it aims to build consistency of data policies across all the publishers in the earth and space sciences. And so this is an effort that has been funded by the National Science Foundation and the Sloan Foundation. We ran a number of meetings where publishers and data facilities came together and are working now on various ways to align policies, to build support for authors and editors, to help them find the right repositories where data should be sent that is part of a publication, to build consistent policies for data citation and so on. So if you want to know more, please contact me. We will have more meetings of COPDESS coming up at major conferences. We're trying to reach out as much as possible, especially during other meetings, earth science and space science meetings. What this really does is increases the development and enforcement of data best practices, because scientists realize they need to comply with what the publishers want from them, and it's really the best enforcement for best practices. It reduces the effort of metadata quality control because people do follow the guidelines better, and more of the small data actually goes into the repositories. Second, that's a bigger one, is EarthCube. Clearly, EarthCube can help substantially in the effort to grow small data into something big. EarthCube, and I'm sure that everybody knows EarthCube. I did not include any explanation about EarthCube. It is an NSF-funded activity, an initiative to build cyber infrastructure across the earth sciences. It's just gone through a first phase of really building governance, getting initial projects funded to build community, to build initial technical capabilities and so on. And where I see the impact on small data is that it advances coordination and collaboration, integration. We have built a community governance that helps with that. But there are also projects funded now that are called integrative activities, and that help. And I will show you, as the last example, is one of these integrative activities that is very specifically focused on small data. And I think that, clearly the EarthCube has had activities called research coordination networks that are helping to build new data communities, build the standards that these communities need. And then it's building technologies, softwares, and so on through projects such as the building blocks that EarthCube funded to structure and transform, integrate data across multiple systems, across domains, and so on. So one of the projects, and this, sure enough, it's one of my projects, is what we call the Alliance Testbed. And it is an effort to use an existing data facility, which is the Interdisciplinary Earth Data Alliance that I mentioned before, as a model for integrating EarthCube technologies that have been developed so far, but reaching out or accommodating small data communities into the data facility, building a structure both socially and technically that accommodates these data activities, data collections, leaving them as the partner, the contact for specific disciplines, but integrating them into really certified data curation services and so on. And I know that ESIP has been working on, there's a working group on distributed data curation. This is very much going along those lines. IEDA has always had multiple disciplines represented, and each one of the systems in IEDA was providing or is providing discipline-specific services. But over the years, we have built up these joint services that have been certified as repository services. For example, the DOI registration, the long-term archiving. So we've become a member of the World Data System and so on, all the stuff that I mentioned before. So what we're trying to do is build this up to grow the alliance to be able to accommodate further partners. So approach is to build on and transition the existing infrastructure to provide more shared services for alliance partners, and to use developments that have already happened in EarthCube, such as through Synergy, the GeoWeb services, or GeoLink as a semantic approach for integration to achieve that. We have a number of partners. We are at the moment now 9 partners, actually 4 new ones and 5 existing ones that have been part of IEDA before. We have intentionally used different types of systems and communities. So we have an existing community data collection, the Metamorphic Petrology database. We have partners that are new data communities that start from scratch, that don't have any data standards, but that we want to help incubate, as we call it, to be able to provide in the future certified data services for their communities. And we have a new data provider. IcePod is actually a facility and an instrument that measures a lot of geophysical data, or acquires geophysical data in Antarctica. We see a lot of benefits. I think I'm running out of time as far as, and also partners really, this is the most important slide with the benefits. I think that the partners, through these collaboration, through these partnership, they are able to enhance their data services, become certified repositories by interacting with the IEDA joint services, and improving their sustainability, ensuring integration with cyber infrastructure developments and so on. For researchers, we intend to ease data management by providing a common data submission hub, by providing a joint data discovery tool and so on. And for the funders, we see benefits in supporting interdisciplinary science, but also creating efficiencies of scale with this approach. So, as my last slide, just a few conclusions. I think that small data can grow big when it's properly curated, documented, harmonized, and integrated. And the essential agent in this process are domain-specific data facilities that can ensure the quality of the data, grow the value, and provide trusted services for reuse, and also engage their communities. Integrations with publications such as through COPDESS can augment the flow of data into the repositories, and partnerships among long-tail communities will allow for better or taking advantage better of existing services for certified data publication and preservation. And activities such as EarthCube can help solve the range of challenges that we have, both across all the social, technical, and organizational issues. So with that, let's focus on data value and not on its bigness, even though you want to go on with big. So thank you.
So now you know why we asked you to give that first talk. All right, thank you, Kerstin. We do have some time for some questions. We don't run too tight a ship here, so. And please introduce yourself.
Thanks. Hey, Kerstin, great talk. Ted Haberman from HDF. One of the nice things about working with you for so long, Kerstin, is that I know that you use language very carefully. And maybe it's because English is your second language. I don't know.
I guess so.
But a couple words that you used a lot were domain specific and scale or scalability. And you also used the phrase domain specific data standards. And I would really, I don't think that domain specific data standards are very scalable. And I think we have a lot of examples of discipline specific data collections that as they grow through time, they become silos. So I would really encourage you to use the terminology domain-specific extensions to data standards, or domain-specific conventions for data standards. And then the data standards are the foundation. They're the soil that the domain-specific extensions grow in, and they allow sharing across of general information across those disciplines. So.
No, I'm glad you make this suggestion. This is something I will take away from it and change. I think it's clearly there are semantics of standards and practices and so on, but thinking of it as extensions kind of emphasizes, I think, the integration of standards such as they come from technology as interoperability standards and so on with the specificity of methods, right? I mean, we have this long-term experience with just the geochemical data, how every method has its own extension, basically, in order to make the data reusable, so I like that.
Any other, one more question? So if you haven't checked the Twitter stream, there's some good capture of things out of Kerstin's talk. Oh, you really want to ask a question, Phil?
Thank you. I'm Phil Young from George Mason. A great talk, Kerstin. I have a question regarding the architecture side, because in your ATP, you are trying to align different data services together. So that's one key issue is about the interoperability, as you also mentioned, on the data level, and also maybe at the service level, maybe upper at the data analytics or data mining level. So how would you consider the interoperability at different levels, and which part is the most important to make sure they are integrated?
Sorry, I didn't understand the last few words.
Oh, the question is that from the data level to the service to the data mining, and to the integrated services part, which part do you think should we focus on the interoperability on? And,
well, I think, whoops, sorry.
Sorry, just setting up.
We starting off with a very distributed and lightweight integration. The systems that exist so far are, quite different in their architectures, in their level of sophistication, let's say. So we're trying to address some level of integration by reusing the synergy architecture right now, in just bringing metadata basically into a common system. But the challenges will lie in the next level, clearly, and that will be it's a research project, right? I mean, we're trying to, what we want to do at the very beginning is really just provide common services and not as much a data integration at the data level. It's the metadata integration level that we're working on.
Okay, let's thank Kerstin once again. And Rebecca Fowler from ESIP Federation is going to introduce our next speaker.
Good morning, everyone. I'm Rebecca, and I get to introduce my buddy, Dr. Gavin Schmidt. Gavin is the director of the NASA Goddard Institute for Space Studies, NASA GISS, which is in New York City, and he's a climatologist and climate modeler. He's also an avid science communicator. He is co-founder of the website realclimate.org, and he's active on Twitter. His handle is Climate of Gavin. And in 2011, he won the AGU Science Communication Award. So I promise you will be entertained and informed today. And this is his first experience with ESIP, so please give him a warm welcome.
Thank you very much. Thank you, Rebecca, for inviting me, and thank you for the opportunity to talk about a little bit of the data that we produce and why we produce it. So I'm going to talk a little bit about the patterns that you see in climate change and the simulations that go with that, and obviously the data issues that come with that. So let's start off with an animation. Pop quiz, satellite or a simulation? Anyone who thinks it's a satellite? Anyone who thinks it's a simulation? Okay, you're correct, but most people get this completely wrong. You can tell because there's no night-day cycle in the clouds. That's a clue. In the real world, there's night and day. What you can see is that the world is complicated and dynamic, and there's lots of things going on. It kind of looks like it's repeating itself, but it isn't ever really repeating itself. It's chaotic in a very technical sense, and it's chaotic in also the popular sense. It's a very complex system. All of the bits join to all of the other bits, and you can't think about it as in a nice little reductionist way. You can't. There's not a box there that's, oh, let me look at the climate in this little box here. You have to have the whole thing, or you have nothing. And that's an enormous challenge to people who are trying to understand this system. And the challenge is clearer when you think about the orders of magnitude involved, right? If you're going from, say, a microscopic particle that might be a seed of a cloud, that's at the nanometer, micrometer level, and you're looking at things that are obviously the scale of the whole planet, that's 14 orders of magnitude that you have to encapsulate within any one theory of climate. That's enormous and totally impossible. If you think about the time scales, you're going from microseconds up to millennia. Again, it's another 14 orders of magnitude in time. These are absolutely phenomenal numbers to be conjuring with. If you think about what we can do in terms of the computational expertise that we have, the computational capacity that we have, I think things have got a little bit better over time. But basically, weather models today, kind of, if you think of this as all the different scales, so it's logarithmic in both senses, weather models cover this little small section from about the size of the planet down to a few kilometers, from seconds perhaps to weeks. Okay, and that's the physics that we can resolve, the things where we can actually know what the equations are, calculate the answer, and then do it. Everything else, all of which matters, particularly the stuff that's faster and smaller, needs to be parameterized. So we call that the subscale processes, the things that we think that we kind of have an idea about, but we really don't know. And everything that we're looking at those scales is somewhat empirically derived and basically subject to a lot of revision as we go forward. Now, if you think about climate models, back in the 90s, climate models only covered that small part of the range. They went out longer, but they had less resolution in the horizontal. So it's a very small part of what's going on. Now, in the 2010s, things have got a little bit better. We have more capacity, so we're kind of like eating into that space of physics. But look how slow that is, right? If we said, okay, well, how long is it going to take before we can cover that whole space with the technology that we have at the rate that technology is increasing? It would be 2100 before we can have an a priori calculation of everything that's going on that graph. Okay? And we would really like to know what's going to happen to the climate before we actually get there. So that's our challenge. What is a climate model? This is a climate model. It's a somewhat old climate model. I agree. We no longer use punch cards, you'll be pleased to know. We do still use Fortran, which comes as a bit of a shock to anybody in high school or in college. I go, whoa. So Fortran is obviously a bit of a niche market now, but it still works. It's still the most effective way of doing it. Plus, I have about 1 million lines of legacy code, which I'm not suddenly going to turn into JavaScript. So, well, we're stuck with it. What can we do? How do climate models work? How do we actually do these things? Well, we try and do it process by process. We try and break the whole world down into individual processes, not individual climates, but individual processes. So take one piece of the jigsaw, right? So this is an aerial photograph of ice in the Arctic in the summertime as you're flying over the Arctic. So you can see that there are ice flows. There's little patches of open water. We can go down there and we can sit on the ice and we can measure everything that's going on. We can measure how much light is coming down, how much light is being reflected, how much of the heat is absorbed by the ice, how much heat is absorbed by the water, what are the properties of the water and the ice, how much is melting, how fast is melting. We can encapsulate all of that in relatively simple code, and then we put it together with everything else. Right? We can now look at, well, what happens in the clouds, right? How do clouds reflect light? How do clouds absorb radiation? How do clouds form and dissipate, right? We can take those processes and, again, put them together. And piece by piece, we can make up a view of the planet and of the system that is made up of all of these different components interacting together. Now, when you do this, you don't end up with a complete picture, right? It would be nice if we had every single piece that was important, but we don't, right? We know that there are things that we don't know, the known unknowns in Rumsfeld's famous phrase. But what we do have is enough so that we can build up a picture of the whole planet. And what we're really looking for is not that level of scale of detail that we put in, but the larger emergent patterns of change and of the climate itself that emerge when you connect all of these different complex nonlinear things together. And you get pictures like this. You get simulations like this. This is a simulation from NCAR, and what you're looking at is the total amount of water vapor in the column, right? So in the tropics, there's a lot of water, as you might imagine, and in the poles, there's not very much. But you can see these atmospheric rivers that kind of spin off from the storms in the Southern Ocean. You can see the really strong points where there's a tropical cyclone, where there's a lot of water vapor concentrated very, very quickly. All of these things are emergent properties, right? They weren't coded in. There isn't a subroutine in this code that says, do an atmospheric river from here to there. There isn't a subroutine that says, do a tropical cyclone. There isn't a subroutine that says, do the tropics now. There are subroutines that say, well, when there's water vapor, you change the radiation like this. There are subroutines that say when there's a gradient, then the velocities are like this and it moves things around. All of the patterns that you're seeing, all of the things that you see and you think, oh, yes, I understand what's going on. All of these things are emergent features of the simulation. They're not embedded within the code themselves. So they come out of it. So what we're doing when we're trying to evaluate these models is we're trying to evaluate them at the level of the emergent process. Right? Not just in the climatology, which you're seeing here, but also in how that system reacts to changes to it and things that affect it. So you can kick the system, and the planet as a whole, 4.5 billion years of climate history, has been kicked in innumerable ways since then. And we're just the latest in a whole series of insults to the climate system that the climate system up until now has been able to cope with quite well, with the few exceptions of the 5 great extinctions and the KT boundary event. Okay, but apart from 5 million years of no life on Earth, basically. It's done quite well. So how can you kick the system? So there are natural variations in the system, for instance, associated with the orbit of the Earth. The orbit of the Earth wobbles, not very fast, thankfully, but it does wobble. It precesses, and the size of the orbit changes over tens and to hundreds of thousands of years. This has a very clear signature in the records of paleoclimate. The sun changes both on a very long time scale. So the sun is about 30% brighter than it was at the beginning of the Earth's history. And also on shorter time scales, on the 11-year cycle, even on a rotational cycle. These things have an imprint on the climate system. Volcanoes have a huge impact when there are huge volcanoes. We haven't had a big volcano for a while. The last one was in Pinatubo, and that had a very clear fingerprint of change on the system. Okay, so you've got smoke, aerosols, ozone holes, deforestation, contrails, and of course, greenhouse gases. All of these things change the basic balance of the ocean. It's not really balanced. It's that they change the basic dynamics of the system. And we can predict what's going to happen when these things happen. And that's the great part of what we've done. We have a huge challenge, right? How do you actually make all those things work and have it be credible? This is how we test how credible these models are. Because when we poke it, and we can see what the fingerprint of that response is in the real world, we can see how well we match that with the models that we've built. So the test that you have with a model is a notion of skill. And people often get this wrong because people think that models are right or wrong. And that's totally wrong. All models are wrong, right? This is a truism that goes back generations. All models are wrong. They are never as complicated as the real world. They are never fully encompassing all the nuances that you would ever find in a real world situation. And that's true for quantum chromodynamics, to orbital dynamics, to climate models. But what you're interested in is not whether models are right, but whether they're useful. Do they give you added value over and above that you wouldn't have if you hadn't used them, right? Are they skillful? If I just put a straight line through something, am I getting a better information by using a climate model or not? That's the test of whether something is skillful, and that's the test that we have to use to say whether what we're doing is worthwhile. So the models are skillful. I'll just give you one example. And I mentioned before, we've had big volcanoes in the system, and they have a very sharp impact on the climate. So what they do is they put in what are called small aerosols. I'll show you an animation of that in a second. Into the stratosphere, those aerosols are white, which means they reflect more sunlight away from the planet than otherwise would have been. And so there's less sunlight coming in. So you're going to see a cooling, right? You're going to see a change in the radiation. So the amount of radiation coming into the system goes down, and we can measure that from satellites. And what you expect is the temperature is going to go down as well. And that's exactly what happens. This is the result of what happened after Mount Pinatubo, which erupted in June 1991. And the red line there is the model response, and the blue and the green are the actual data as it happened. And in fact, we predicted, my group before me, my ancestral group. Does that make sense? We actually predicted this in October of 1991, right? So the volcano went off in June 1991. By October, they'd already done the simulations that predicted that there would have been a cooling of between about 0.3 and 0.5 degrees C over the next 2 years, and that's exactly what did happen. And that was done with a 1980s era climate model, and now the models are much better. But you also see other things. There's interesting things that go on. One of the things that happened in the winter after a big eruption is that the wind patterns in the northern hemisphere shift so that they're more zonal. So there's more wind kind of going into Europe during the wintertime. And in fact, you actually get a warming pattern in Europe the winter following a big eruption, statistically speaking. And so that's that red patch over there. And again, the models produce that. They predict that is exactly what you would see based on changes in the temperatures in the stratosphere, changes in the winds, and those winds propagating down. There's an enormous amount of different aspects of the model that are all fitting together to produce these results in the models. And the whole thing gives us an evaluation of the skill of those models. So here are some more atmospheric particles. aerosols. This is an animation from Goddard Space Flight Center. What you're seeing in the different colors are different kinds of aerosols. So the orange stuff is dust. That's mainly coming from the Sahara there. The white stuff is sulfate pollution from burning sulfurous coal. You can see whiffs of that coming off of Europe. You can see blue where there's sea salt particles, you know, that kind of salty taste you can taste in the air on the seashore. Those are small particles, and those are being modeled in this simulation as well. You can see the pollution coming from China, and you can see the green organic carbon and black carbon pollution that's coming from fires in Indonesia. So each of those red dots is a fire in Indonesia in 2006, 2007, all of which are producing an enormous amount of black carbon, soot, and organic carbon aerosols. You can see that there's the tropical cyclones there going into Japan there, and again, very large amounts of sea salt being associated with them. This is a fascinating animation because it demonstrates how closely tied all of these aspects of the climate are. Really, every single thing is connected to every single thing. Each of those particles, each of those fields in the atmosphere changes the amount of radiation that's going in and out. It changes the cloud formation, and you can see that the climate itself is moving these particles around and putting them into these marvelous patterns and features. And if you're paying attention to Madagascar, there should be a volcano erupting any minute now. There we go. Yes. Okay. And so you can track the impacts both of natural changes from volcanoes, but also from the human-made changes from pollution and other sources like that. So we can test it on slightly larger scales. We can test these models, for instance, over the 20th century. Right? This is an animation of the model over the historical period since about 1850 to the present, and then there's the observations. What you're seeing right now is the ups and downs of weather. Weather is not predictable tens of years in advance. And so what you're seeing is that the weather in the two simulations, and the simulation and the observations, are not the same. They're not correlated. But what you're seeing as you get to the end of the century is that there's a pattern of change that goes beyond what just the weather is doing. And that pattern of change is driven by the anthropogenic, the human-caused forcings, drivers of climate change that we've actually been putting into the system. Now, how do we know what it is that we've done to the system that's creating this pattern? Well, we can break it down. This is an animation that we worked on with Bloomberg Business News, particularly Eric Roston and Blackie Mazzoli. And what we did was we did what's called a classic detection and attribution study. Okay, so here's the observed temperatures warming up over the 20th century. Here are the different effects of natural things that are going on. So these are the volcanoes that went on, and so the orbit is changing, the sun is changing. None of those things really add up to what's been going on. And now let's put in some of the things, the human-caused changes. Okay, land use change. We deforested. What impact does that have? That has a slight cooling effect. Ozone pollution in the troposphere has a slight warming effect. Aerosols, those sulfate particles, nitrate particles, have a slight cooling effect. Greenhouse gases, dominant among them is carbon dioxide, have had a warming effect. And in fact, slightly more of an effect than you would have expected, than you would have seen in the real world. But you start to put these things together, and what you find is that the addition of all of those human things actually lines up very nicely with what actually happened. And if you combine the human and the natural variations, you actually end up with a really good fit to what's actually been going on. Right, so this is how we do that attribution. When people ask us, how do we know that it's greenhouse gases that are causing most of the warming since the 1950s? This is how we show that, right? When people say, well, how much of climate change is man-made? Right now, all of it is, because the natural tendency for climate in the last 50 years would have been towards a slight cooling. We have not seen a slight cooling. All of the warming that we've seen is, in fact, anthropogenic. And now, this is a slide for you guys. How much data was in that animation? Okay, I actually calculated it. It's 6,204 bytes. Okay? How much data did I have to process in order to produce the data on that graphic? It's about 7 billion bytes. Well, 7 billion times that, right? So the data compression ratio in that animation is about 1 billion to 1. Okay, that means for every one piece of information you saw on that graph, and even that I could have reduced it a little bit because there's a little bit of serial autocorrelation there. There was 1 billion pieces of information that I had to calculate. There's two corollaries to that. One is it's really hard to take big data and to compress it to the size that you can tell a story that somebody else is going to understand. I can show you an animation which had a lot more data, right? The aerosol animation, that had a lot more data in it, right? But there wasn't an obvious story, right? I had to walk you through that. I could still walk you through that and lead you to seeing some of the aspects of that simulation. But if I want to make a clear story, I want to make a narrative that normal people can understand, I have to do much more. I have to compress it down even further. So there's an enormous amount of work in taking big data and making meaningful narrative stories. The second part of that is that means that there are so many more stories in these data sets than we have even come close to trying to bring out, right? Even if, like, you know, the redundancy in this data is enormous, but there's more than one story in those billion data points. How do we work with this data to bring out the interesting stories? And for all of the databases, for all of EarthCube and for all of DOIs, we have not come close to dealing with this problem for earth science data. We have an enormous challenge ahead of us to use this data in a way that releases the knowledge and the science and the connections that we've already calculated, but we're just ignorant of. Now, why do we use models? I alluded to it earlier on, but I think this quote really captures it. If we had observations of the future, we obviously would trust them more than models, right? But unfortunately, observations of the future are not available at this time. Right? This is the key thing. We're trying to get a head start on what's happening. We know that we have predictability because of the basic physics of the system. It's not totally hopeless. It's not totally chaotic without any predictability. But to make predictions, you need models because we have no observations. And those models need to be evaluated and they need to be credible. It's a tough thing to do. I've tried to demonstrate a little bit why we think these models are credible, but you should actually see what they're predicting for the future, right? So these are predictions with that same model that I showed you out to the 21st century. But we don't know many things about what's going to happen in the future. We don't know how the economy is going to go. We don't know what's going to be invented, the technology, and we don't know what the society is going to do about the emissions that we're putting in. So we do different scenarios. We could say, okay, well, you know, we could be aggressively mitigating. So this would be aggressive mitigation would be something along the lines of what people aspired to with the Paris negotiations last month. So that's not going to happen. The business as usual, that's kind of going hell for leather, doesn't matter what we do, burn it all, burn it all, burn it all. Okay? It's very red. Okay, so that's bad, right? Red, okay. But it's a trick, right? You know, I just made it red. I could have made it any color I wanted. Anything that's kind of totally saturated is more than 4 degrees C warmer than present. Okay, do we know what that means? Do we know what 4 degrees C means? Kind of technically we do, but really, do we feel it? Do we viscerally understand what 4 degrees C warming in a planet is? No. So in this room here, since we've been sitting here, the temperature's gone up about 1 degree. Nobody has died, nothing has become extinct, the chairs haven't melted, right? We can totally deal with 4 degrees, right? Get a little bit sweaty, but it'll be fine. Planets have a different scale. Remember I mentioned the orbital forcing earlier on? One of the big signatures of that orbital forcing is the coming and going of the ice ages. 20,000 years ago, we were in the middle of a big ice age. Ice sheets came all the way down to as far as New York City. Anybody who lives in New York City? Anybody who lives in New York City? Yes, okay. Did you live in Brooklyn? You look like you live in Brooklyn. Okay, oh yeah. So had okay. No, that's good. Anyway, had he lived in Brooklyn, he would obviously have gone to Prospect Park. And in the middle of Prospect Park are the terminal moraines for the last ice age glaciers, right? So it didn't get as far down as DC or Chesapeake Bay, but it's pretty close, right? Around here would have been tundra, basically. 20,000 years ago, ice all the way down to New York, across the whole of North America, sea level down maybe 400 feet from where it is now. What was the global mean temperature change? Shout out a number, come on. 4 degrees. Oh, good, whoever that one person was. Yes, it was about 4 to 5 degrees colder. That is all. Right? 4 to 5 degrees for a planet is the difference between an ice age and the present. 4 to 5 degrees warmer is like another ice age, but in the other direction. This too will be a different planet. Okay? Are we going to end up with some serious amount of mitigation that ends up not quite as bad as the worst case, but probably not as good as the most optimistic case? One might hope so. But it leaves us in an odd position, right? You know, I'm a mathematician by training. I'm a climatologist by profession. I'm not a public figure, I'm not a politician. And yet, Sherwood Rowland said this. Sherwood Rowland won the Nobel Prize for discovering the chemistry that leads to ozone depletion in the stratosphere. And he said this, he said, what's the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is stand around and wait for them to come true? I'm standing on a stage, I'm not standing around, but what you have in terms of the data issues, the data access, our ability to tell stories with these data, this is the manner, this is the way in which science has to get out from the silo to the larger world. If we are not just to stand around and wait for these things to come true. Thank you very much.
Thank you, Gavin, as usual. We do have time for some questions.
My name's Sean Barbary. I'm a ESIP student fellow, and I was actually curious if there's a place where we can access that visualization of warming that you showed, because I have some relatives I would like to send it to.
Yeah, it won't work. The Bloomberg animation, if you Google what's warming the world, Bloomberg, you'll find it. It's an interactive D3 shockwave thing. It's a very well done piece. The Goddard Space Flight Center aerosol animation, that's on their website. Google aerosol Goddard Space Flight Center animation, and you'll find that. And pretty much everything else is also available. If you need to find it, or you can't find it, just send me a link. Send me an email.
This is Dave Folker, and I want to thank you for a very stimulating talk and ask the question. There's a lot more than data compression involved in telling a good story.
Absolutely. And
you had a very good, a good story, a good way of telling the story, I thought, in the entire talk. What activities do you think are the most helpful at this juncture in developing the storytelling skills, aside from the data compression ones? In other words, is there Is there cause for optimism in how stories are being told generally? And could you point us toward examples of that, please?
Right. So that's a great question. There's actually quite a good book that just got published by Randy Olson, who started off as an evolutionary biologist, but then gave up academia to go to Hollywood to make movies. And he spends a lot of time thinking about communication, building narratives. And one of the things, so he's got a new book out, which is called Houston, We Have a Problem, which is all about telling stories in science and helping people do that. And one of the things that he points out, or he's kind of like encapsulated, which I think works very well, is that almost all stories have a very basic structure. They have something happens and something else happens, but, oh my God, now there's a point of tension and therefore there's some resolution, right? So there's that and, but, therefore resolution, okay? Almost all stories have that same thing, right? Casablanca, and the war, and we're stuck in Casablanca, but we need the visas. Therefore we have to now have complicated love triangles and all the rest of it, okay? So obviously I'm not a screenwriter, but that basic structure is a very it's a very universal theme. And we spend a lot of time in science communications just doing the first part of that, just doing and look at this, 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 and it goes nowhere, right? Building in the struggle, building in, this person was interested in this, but they had to go to Antarctica and suffer tremendous hardship in order to get it. And therefore they came up with this data and they came up with this marvelous thing, right? Those kind of stories do much better than, hey, this is the answer from the Vostok ice core. Right. So telling stories there is a lot of help available for helping people tell stories, helping people communicate their story. And Randy Olson's book is a great intro to that. But mostly, it's practice. One of the things that people say, oh, you gave such a good talk, and I always think that they're crap, but other people seem to like them, so that's nice. But my first talks were terrible. My first talks were all text and graphs, and you just don't realize how terrible that is when you're trying to get across to an audience. Graphs. Most of us have science backgrounds here. We've been trained to look at a graph and pull out what's important very, very quickly. Most people in the world have no clue what you do when you show a graph. They're spending all of their time looking at totally extraneous things, and they don't even see what you see. So if you put up a graph, it takes about 20 minutes to explain a single graph and have actually everybody understand what it is that you're seeing, right? That's a disaster, and our like collective skill set at telling our own stories, which is often has been beaten out of us by the time we finish a PhD or something, is kind of bumping along at zero. And I think we can do a much better job. But we have to want to try, and we have to want to listen to people. So your relatives, okay. I guarantee that just sending them a link is not going to help at all. Because they're not looking at it in the same way that you're looking at it and you're thinking, well, look, and they're looking at it and they're going, I don't even trust those scientists. What does that even mean? That fuzzy thing. What is that? What is that? A line that's not proof, right? Because they're looking at it very, very differently. The best way to talk to somebody where you have a trust built up, right? They don't think that you're the worst person in the world. So if I went to talk to them, they think I was the worst person in the world, right? Some of them tweet at me. I know. But you have a level of trust. You say, okay, look, what is you have to get to the real problem. And the real problem is not that they don't believe the scientists. The real problem is not that the graph was in the wrong color. The real problem was not that the animation wasn't interactive enough. There's another problem, right? It's a question of values, right? What they see when you show them a graph is a rejection of some deep value that they hold dear, right? And if that's the way it's going to go, you're never going to get anywhere. Right? So if you're talking to somebody, you have to find the value issue where you can actually kind of dig down and see what's going on. And stories can help with that, because stories can help demonstrate that we share very many of the same values. We all love our children, and well, mostly, you know, and we don't want people to die, and we would all like to have a nice life. I mean, once you build it from shared things, you can go forward. Now, you know, there's some communities I can't talk to because, you know, I'm a liberal Jewish atheist from New York City, right? So if I go to Texas and try and tell people about climate change, I'm totally the wrong messenger, right? Because we don't have any shared values, quite frankly. But some people do, right? So Catherine Hayhoe, right? So, you know, she married an evangelical pastor, and I don't know if you saw Years of Living Dangerously. She featured on one segment there, talking to, you know, townsfolk in Plano, Texas, and she's one of them. No, she's from Canada, so she's not quite one of them, but she's almost one of them. And so she can talk to them in ways that don't threaten their kind of who they see themselves as, right? And a lot of times we think, oh, more science, and really we want to have less science and more cultural understanding, and that might take us a lot further. Okay. Oh, yeah, one more. Sorry, that was rattling on there. I apologize.
I forgot my question.
No, excellent. Yes.
Gavin, Dave Jones with StormCenter Communications. I was just wondering, you were showing the great animations at a global scale, and what some people need to see before they really believe what's going to happen is what's going to happen in their neighborhood, what's going to happen in their region, how is it going to impact their gardens, you know, things like that. When do you think we'll get to the point with climate models and predictions out to the future, maybe to 2100, to show the impacts at much more local levels? Yeah, and it's not going to come from the models. Impacts at local levels you can see because they're connected across a wide area. If you live on the coast, you can see the impacts of climate change and sea level rise now, right? Every time there's another king tide, oh, what a surprise, in Miami or in Newport. You know, you just, you know, why are these happening more and more often? Right, like Venice, why is it flooding more and more often? Right, it's sinking, the water's going up. Like it's clear. Changes in people like the gardens, right? You know, the hardiness maps. You know, the classification that US GS puts together for, you know, what you should be growing in what climate zones. They've shifted 2 zones since they started making those maps, right? People who spend a lot of time in their gardens or on farms and things, they notice these things, and you don't need the model to tell you that something is going on. Right. The models themselves, by the time they get down to there, it will be too late. Right. So don't rely on, if you need to make that point, then you have to connect it in some other way. The models are not going to help you.
Right. Let's thank Gavin once again. Before we go into the break, I want to do 2 things. I was remiss, of course, I always forget something. Could the ESIP student fellows please stand up? All right, so look around. This is the new group of student fellows, and you'll see them active in the technical sessions. Please introduce yourself to them. Offer them jobs, things like that. I know this guy in particular is looking for one. So I just wanted to do that. The other thing is, before you get up and go, well, as you get up, Erin has requested that you, as you move out into the reception area to get your coffee and tea and stuff, introduce yourself to someone you don't know and exchange names, just to get the networking and get the collaboration going. All right? And we'll be watching you. If you don't introduce yourself, you're going to be in trouble. All right, thanks everyone. Come back at 11. All right, everyone, can you grab a seat? I'm hesitating to use my professor.
Audio test. Test. Test.
Working on.
Check, check, check. Shit. Hey, check, 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 check.
Right, everybody, please take your seats. We're waiting for sound.
Check, check, check. Well, you know what?
Exactly.
Somebody's switching the moment. Yeah, so that's 220 to 240. Nobody touched it. It's right here. What does it say? It's right here. No, somebody just flied it because of 120. And that's a normal here, right?
Hey.
We can't go without sound because there are people on the WebEx and we're broadcasting live through YouTube. So be bad.
Check, check, check.
I know. Talk amongst yourselves.
Hey. Check, check. Check, check.
Someone turned off the sound.
Check.
Don't seem to be able to get it back on.
Check, 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 check. Hey.
That's it.
Check.
Every minute.
Hey.
We're doing so well.
Check.
Yeah. Sure. It's all the mics, probably not. It's like the
1, 2. Check.
like a secret mic.
Anyone got any jokes? Interpretive dance. Juggling.
Check, 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 check.
He's calling someone that's got
Check,
what?
check. Hey,
Could be
hey.
very scary.
1, 2.
I mean, I can.
1, 2.
I project.
1, 2. Hey, nothing?
But then,
Hey. Check, check. You know what we need to do? We need to put up our speakers. Do we have power speakers? Huh? Hey, I'm trying now. Hey, 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 hey. There's nothing. Okay.
It's just working. So
Yeah.
something like catastrophically happened. Now we have 2 people.
Hey, 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 hey. Check, 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 check. Check 1, 2. Hey. Check 1, 2. Check. Check, check. Check 1, 2. Hey, 1, 2. Check.
Hey, one more.
Two speakers, two small speakers at this time. Yeah, you and Lisa, please. Just bring the 2 speakers. I'm going to check this. Total commercial sound, please. There's no sound. Have sound.
Is there a verdict?
One here. There's nothing we can do right now. Only thing we can do, they're gonna get speakers. Instead using the house sound right now, they're gonna put 2 speakers in front. Just wait for them to bring them in.
anybody, I'm not sure if somebody attaches here. But to me, it's nothing. Looks fine. Volume is up. You gotta have one with quarter inch. Yeah.
Turn that
You're on it to get it done.
Yeah, sometimes they don't have panels that are going to light up along the wall.
There's a
Or
volume
off the
here.
board, so I don't know what's
I already play with check. It's nothing.
Yeah, I think we have just like a.
Yeah, well, Huh? Not sure. We know right now we don't worry about the wall. Let's run the cables, right? Once you're on the street, we have a return.
You get it done.
Yep.
This is not. This has nothing to do.
Oh,
So we do it one time. Here.
You can just.
That's what I'm saying. I don't really see a return one. Which one is a return? They don't have a return. That's fine. Go ahead and on the cable. Just
hours of silence, right. Experiment that we were conducting without your permission, courtesy of the hotel. Thanks for being patient. Hopefully you made some more friends, wrote some proposals, answered some emails. We're about to get underway as soon as we get sort of people settled. And is that? Okay, so I'd like to introduce Lindsay Barbieri, one of our student fellows, to introduce our first speaker.
So let's see, is it working? Excellent. Okay. So I'm Lindsay Barbieri. I also go by Bar, and I'm one of the student fellows here at ESIP. I've been working for the past year with the Agriculture and Climate Cluster, and I'm now transitioning into the Data Analytics Cluster and helped to found the Drone Cluster here at ESIP. All very exciting. I'm also a graduate student at the University of Vermont, where I work with the Spatial Analysis Lab. The Spatial Analysis Lab has an unmanned aircraft systems team that I am happy to participate in. And in addition to that, also hosts many mapathons for crisis mapping after natural disasters. And it was through this sort of intersection of drones, natural disasters, and thinking about humanitarian efforts that brought me to Dr. Patrick Meier. So Dr. Patrick Meier is an internationally recognized expert and thought leader on humanitarian and technology robotics. He's worked in numerous countries, ranging from the Philippines to Haiti and many, many places in between, and worked with many international organizations such as the UN and the World Bank. He's given many hundreds of talks across many countries, and we're very excited to welcome him now to talk at ESIP. And it's my great honor to introduce Dr. Patrick Meier.
Thank you so much for the kind introduction, Lindsay, and thank you to Aaron as well, and Peter and team for kindly inviting me to speak this morning. It's a real pleasure to be here. This is not an area of expertise in terms of information earth sciences that I'm very familiar with, so it was really neat to sit in on some of the presentations this morning. So thanks again for having me, and in the interest of time, I will jump straight into the presentation. I've been asked specifically to give a quick overview of the aerial robotics space, i.e. UAVs, so-called drones, in the context of big data and humanitarian applications. And so I'm going to start with a quick sort of overview of where we're at in terms of the industry, because it's really exploding. As I'm sure many of you may have been following the news over the past few years, given that the price point has fallen so drastically and the technology itself is becoming more reliable, safer, more sophisticated, and much easier to use, we're just seeing a kind of democratization in terms of access to this technology, whether it's fixed-wing UAVs that look like small airplanes or multi-rotor UAVs that look more like helicopters with multiple propellers. We're really seeing quite an explosion of this technology, and it's not going to stop anytime soon. You speak to industry experts in this space, and this curve in terms of the number of consumer drones being sold every year is going to continue increasing until further notice. So despite all the challenges and the negative sort of connotations of drones and so on, as an industry, as a robotics industry, because UAVs are aerial robots, this robotics industry is not going away anytime soon. And as you have more and more of these aerial sensors up in the air, that translates into more and more aerial data as well. So if you go to a website called Travel by Drone, you'll see literally thousands and thousands of aerial videos that enthusiasts, professionals, amateurs have uploaded based on the content that they've generated. So in a way, it is user-generated content that we often ascribe to social media. So in many ways, it is aerial social media. You see aerial pictures and aerial videos on Flickr, on YouTube, on Twitter, on Facebook. It really is just exploding, and not just in the US, but in Europe and many other places around the world. Now, this new source of potential big data, quote unquote, is not evenly distributed. So you go to places like Latin America and Guyana, and there's not much traffic there yet. But if you actually look a little deeper in the beautiful rainforests and jungles of Guyana, you'll find that there's an indigenous community, the Wapichanas, that have been working with some friends of mine to build this simple fixed-wing UAV in the middle of this rainforest. forest. And this is actually a video of their first test flight from a while back. I thought I'd share it with you. If you're here. Nobody said robotics was easy. But if at first you fail, try and try again. So even in Guyana, where at first sight there is no use of robotics, you're finding local indigenous communities using these kinds of platforms for data collection, sensors, and so on. In this case, specifically because they're very worried about illegal deforestation and illegal mining in their beautiful jungles, and they're looking to use this aerial data to document this this crime and share that with the government and advocate the government to actually do something about it. So it can be a very powerful way to witness and provide testimony. Now, I first got more involved in the UAV space in 2013 when a high-end Category 5 cyclone, or typhoon rather, Typhoon Haiyan, devastated the Philippines. I was seconded to the United Nations to support their relief efforts. And within a few days of landing in the Philippines, I'd come across half a dozen different UAV teams who were on the ground with small UAVs, small drones to support relief efforts to collect imagery on disaster-damaged areas and so on. And that was unprecedented. I've been working in the humanitarian and technology space for almost 15 years now, never seen that much response in terms of aerial robotics. But I also quickly realized that most of these teams did not know about each other. Most of them weren't even sharing imagery with each other, let alone government, local communities. And most did not know how to plug into the international humanitarian efforts in terms of sharing their imagery with the UN in the right formats and so on. And I still remember going online in Manila and on Google and going, code of conduct, drones, UAVs, disaster response, and finding absolutely nothing. And that got me really worried because I didn't have something I could share with these teams and say, listen, this is how you engage with local communities. This is how you get permissions for flights and so on. And these are the best practices and lessons learned. So a few weeks after leaving the Philippines, I launched the Humanitarian UAV Network, or EADA'S. And the first thing that I did was start drafting a code of conduct, not because I'm an expert, but because nobody else had done it. And I figured I might as well draft the first version and then ask for experts to help me actually improve it. And since then, over the past 2 years, the draft has gone through dozens and dozens of revisions in very close collaboration with the United Nations, the American Red Cross, the international community of the Red Cross, the European Commission, the World Bank, the World Food Program, the UN Refugee Agency, and so on. So now it really has become the leading international code of conduct for the responsible, safe, effective application of aerial robotics in a wide range of humanitarian settings, not just in disaster response, but all cycles of all phases of the disaster cycle, as well as development applications. And we're increasingly now looking at environmental applications, conservation applications, and so on. So while Humanitarian UAV Network is what we started as, we're increasingly just going by UAVators because that's far more open in terms of moving forward in the application of this technology. Just a few quick notes. Our advisory board includes a number of humanitarian organizations that you see listed here. I've already mentioned a few of them, like the UN, the World Bank, the American Red Cross. We also have technical advisors that come from Google, CNN. CNN Air now has a whole UAV team for media coverage, Google X, DJI, and many other leaders in the space. We've already been recognized by the UN as a credible initiative, a credible organization in the space, and we're really looking to learn more from other applications of aerial robotics, such as applications in your fields of expertise. There's a lot that I've learned from the conservation space and from other spaces. I'm very, very keen, very pleased to hear from Lindsay and others that you do have a drone cluster in this space, and very keen to make this the start of an ongoing relationship where we can share lessons learned, best practices, what technologies are out there. And also, as we were just discussing during the break, the extended break, there are crossovers between your fields and disaster response, right? We've done some work in the Philippines on food security with UAVs. After Typhoon Haiyan, one of the UNDP, UN Development Program, wanted to assess the impact of the typhoon on agriculture. And I was on a call a few weeks ago with the World Bank in the Pacific, with El Nino and so on being a top concern of theirs. They want to use UAVs and aerial robotics to assess impact on agriculture agriculture after cyclones and so on. So I'm really, really excited to be here and very much look forward to this being the first of many conversations. I want to now bring it down to earth maybe and give you some very concrete applications and examples in the real world, as much as firsthand as I can, on how we've applied these technologies over the past year. Cyclone Pam was a Category 5 cyclone that devastated the islands of Vanuatu off the coast of New Zealand and Australia. This was a Category 5, so we're really talking about a major disaster. This was back in March. And the World Bank activated UAVators to carry out a humanitarian UAV mission there, to carry out aerial surveys of the disaster damage. So I recruited 2 teams from Australia and New Zealand from our roster. We have a dedicated roster of about 500 UAV teams in about 60 countries around the world. So we've got quite a bit of global coverage, and we can activate these teams literally within hours, which is what happened in this case. And our task was to complement the field-based surveys that were taking place on the ground in Vanuatu. This is something that happens with all major disasters. You have teams on the ground, walking around, driving around, assessing the impact of a disaster on infrastructure, on buildings, shelters, houses, and so on. And our task was to complement, not replace, but to complement that assessment through aerial imagery. And one of the reasons, or there are several reasons why we were asked to do that. One of them is that these field-based surveys can take a lot of time, can be quite expensive. They often suffer from some serious data quality issues when you've got 50 people trying to fill out the same surveys and interpreting the questions differently. Just to let you know, in the case of Vanuatu, 30% of the field-based surveys that came in we had to throw out because of data quality issues. And you're limited by the laws of gravity, right? You're on the ground and you're assessing what's in front of you. You can't see infrastructure damage on the 2nd floor, the 3rd floor, or other structures that are higher up. So our task was to identify fully destroyed shelters, houses, buildings, partially damaged houses, buildings, as well as largely intact, just like the field teams were doing, so that we could triangulate and complement that. We primarily use multi-rotor UAVs. You see here some hexacopters, as well as quadcopters with 4 propellers. It's important to note again that these are aerial robotics, and I'll show you a bit more on how this is all done with aerial robotics and programming these flights. The first thing that we found when we landed at the international airport are cargo aircraft, C-130s, military aircraft from the Australian Defence Force providing relief supplies. This is obviously going to happen in disaster response, as well as passenger aircraft. So this was a very complex airspace, and it meant that we had to work very closely with air traffic control to coordinate our flights at the same time that you had international flights landing and taking off, right? Safety is the #1 priority when you use UAVs in whatever situation, whether it's environmental, development, or humanitarian. So we set up some really very clear coordination mechanisms with air traffic control, where we had direct access, phone access, radio access with air traffic control in order to coordinate our UAV flights with these passenger and military aircrafts. We had a whole process where we would submit our flight plans and so on. And because these are aerial robots, what we would do after our flight plans were accepted by the Australian Defence Force and Air Traffic Control was program the flights for the following day. And so a lot of your time is actually not flying, although maybe that's the exciting part. A lot of your time is getting the permissions and then programming the flights, because these are autonomous systems, autonomous intelligent systems. You literally press a button and it follows a flight path and then comes down and lands itself. That's all you do. So in fact, it can be quite boring. Now, after data collection, humanitarians, I'm sure you as well, are not just interested in pretty pictures. You want very concrete answers to very specific questions, because you have very specific information needs. One of the challenges in the context of big data, as part of the theme for this event, is this overwhelming amount of information that gets collected. So recent research by Texas A&M University has shown that a single 20-minute flight, UAV flight, can generate up to some 800 high-resolution aerial images, and it takes an expert analyst at least a minute to analyze an aerial image. So you're talking about a single 20-minute flight generating 13 hours worth of analysis time. And by the way, we carried out over 150 flights. So you do the math in terms of how much time would be required to analyze this big aerial data. Now, it turns out that our World Bank partners, even though they'd commissioned us to do this aerial surveys, had no time. They were already overwhelmed with other data sets. So what we did was we turned to other platforms and partners, specifically the Digital Humanitarian Network, a network that I co-founded with the UN a few years back. And members of this digital humanitarian network, like the Humanitarian OpenStreetMap team, have thousands and thousands of digital volunteers available online who can mobilize online literally within minutes to analyze analyze data. And this is exactly what we did in this case. We took all the nadir imagery and pushed that to the Humanitarian OpenStreetMap platform and had volunteers trace which buildings were fully destroyed versus partially damaged versus largely intact. You see some of the results here. Red are basically fully destroyed and yellow partially damaged. We also collected oblique images, which are aerial images that are taken at an angle. And this is quite useful for disaster damage because you want to see whether the structures of a building have been damaged rather than just the roof part. And so we collected thousands and thousands of oblique aerial images. And there again, our World Bank partners were overwhelmed, did not have time to analyze this imagery. So we crowdsourced it. And what we did with oblique imagery is we sliced them up into micro images and then pushed them to a platform called Micromappers, which is an open source platform I've been developing over the past couple of years in partnership with the United Nations. And we invited hundreds and thousands of digital volunteers to do the same process, trace the houses within Micromappers. And you see some of the results here. Blue traces, again, are largely intact. And we really are talking very high resolution aerial imagery. You're not going to get this kind of resolution with satellite imagery, at least right now, that's commercially available at such a low cost as well. So this is all very important information, and then we posted it on a map, made it available to our World Bank colleagues, and so on. And the reason you see multiple traces here, just by the way, is because we would show every picture to at least 5 different volunteers for quality control triangulation purposes. And only when there was overall consensus would we prioritize that data point and have it mapped. After the relief efforts, we decided to take it a little further because crowdsourcing alone is not going to win the big data battles. So we worked with some computer vision students at EPFL in Lausanne in Switzerland who are also experts in machine learning. And we took all the traces that you see here, all the traces that these digital volunteers, I call them digital Jedis, made on these images, thousands and thousands of them, and used machine learning and computer vision to train the algorithms to be able to identify whether an oblique aerial image has a building, a house, a shelter in it or not. And then the next step is to obviously try and see if we can teach the algorithm to distinguish between destroyed versus not destroyed. And this is not just an academic exercise, also it makes for a good publication and so on. As all of you know better than most, with El Nino effect being the strongest, as far as I understand, in some 50 years, with potentially a disproportionate impact in the Pacific, you know, the Vanuatu, Tonga, the Solomon Islands, the Marshall Islands, Fiji are potentially in the middle of the target of future cyclones. So the World Bank and our partners at Harvard and others at EPFL are really racing to try and develop these algorithms in time so that we can do automated feature detection of buildings, shelters, of features of interest for disaster damage assessments. And increasingly, you can get live aerial videos directly from UAVs. So this is aerial videos from Vanuatu. And what we're doing is we're working with computer science students at University of Southampton to crowdsource the analysis of live aerial video footage in near real time. So what you see here are hundreds of volunteers who are clicking in real time on the video footage in areas where they see some disaster damage or potential disaster damage. In every area where there's about 80% of these volunteers who are clicking, we light it up as a real-time heat map. I would love to talk to you during the break and after as well. What kind of applications might be relevant in your field for these particular tools? And you have access, by the way, to the Digital Humanitarian Network. Thousands of digital volunteers who are really eager all around the world, every time zone, to help out on really meaningful projects, whether it's humanitarian, development, environmental, or otherwise. I'm going to end now, just to make sure I have about 10, 15 minutes left, with the second project, and then just wrap it up. Quite different. This is in Nepal. As you know, in April last year, there was a major earthquake that struck Kathmandu, just outside of Kathmandu, really devastating the area. And this is a mission that I spearheaded in September with a number of partners, DJI, Pix4D, in close collaboration with the University of Kathmandu and a number of Nepali NGOs. We were invited by a local community to carry out aerial surveys, and I'll tell you a bit more about that. What we did do, though, is something I want to highlight with UAVers. We don't just do projects and then leave. One of our very core areas of priorities is to actually train our local partners on how to use aerial robotics for disaster recovery, disaster response, disaster preparedness. So not only do we spend time transferring the skills and transferring the knowledge that we have, but we also transfer the technology. Thanks to our technology partners like DJI, DJI, we were able to donate 10 DJI Phantom 3s, which are, as far as I'm concerned, the best multi-rotors, accessible multi-rotors out there. They're just $1,000 really, and they're incredibly sophisticated. And so we were able to donate that and transfer the technology as well, so that we can empower our local partners, who are, after all, going to be the first responders when the next disaster happens, to use this technology themselves to carry out aerial surveys for disaster damage assessments and so on. So we spent a couple days on campus at Kathmandu University training our local partners, faculty, students, NGO representatives, government officials, and so on. And this is what a Phantom 3 looks like. You have direct video relay, about a few miles really. You can fly it out and you can program it and do all kinds of really interesting, powerful flight plans and so on. We also had time to train a few mini monks along the way. You know, a lot of people think that local communities are going to react negatively to UAVs, and I've yet to find an example. I've been surveying dozens and dozens of case studies over the years, and I have firsthand experience as well, whether it's in Nepal and Vanuatu or elsewhere. Adults and kids alike are intrigued. They really want to understand, what is this technology, how can it be used? And so community engagement is a really big part of our guidelines, our code of conduct, is how do you engage with the community? And it's not an option, it should be, it's a requirement that you have conversations and partner with local communities to use these platforms in their countries, in their villages, and so on. So the actual mission I spearheaded was with these different teams. Again, in September, after we did the training, it was a way, in a way, it was for our local partners to reinforce what they had learned, to go, get off campus now and actually do a real-world survey. So I could speak for hours on this one mission, so I'll point you to my blog at irevolutions.org, where you'll find more pictures, more examples, videos of the mission, and I'll just give you some highlights over the next 5 minutes. The first thing to note is we didn't invite ourselves there. We were invited by the local Community Disaster Management Committee, the CDMC, of that area. This is an area just outside of Kathmandu called Panga, which was one of the hardest hit areas after the earthquake. And the CDMC there was desperate for more up-to-date, better data to inform their reconstruction and rebuilding efforts. So we worked directly entirely with them throughout the entire operation. They were directly involved in programming the flight path that you see here. I think I have a better picture. In this case, we used a smartphone app from Pix4D to program the flight path. They would be doing that. They would be deciding where we would take off from and land, how high we would fly, where we would fly, and so on. So they were absolutely instrumental to the entire mission. And as we packed up that night, we had spent the whole day mapping. The head of the CDMC came up to me and somewhat nervously said, listen, you are coming back tomorrow, right? And the fact is, we had spent one day and allocated one day because that's what we thought was going to be necessary. It turns out we hadn't finished the mission. The head of the CDMC told us, listen, there's so much more that we need mapped, you have to come back. So threw a bit of a wrench in our plans, but it was the best possible wrench, right? That's when you know you're at the right place at the right time, and this is demand driven. You're not just throwing data just because it's sexy and so on. People actually needed this data. So I ended up canceling my flight back from Nepal and staying on a few extra days, and we spent the next day, the full day, without even taking a lunch break or anything, mapping from sunup to sundown. And this is an area of Panga that we surveyed with the UAVs, 30, 40 flights easily over the course of 2 days. And this is the result. This is now the highest resolution aerial map of Panga ever made. And just to drive the point home, again, you really are talking very high resolution. If you compare this with what our local partners were working off, namely Bing satellite imagery and Google Earth imagery, it's quite a different setup, right? You're talking about completely out of date, blurry, and frankly not very usable imagery. So this was a big game changer for them. And with aerial imagery, you have the advantage of creating 3D models. You can use software that already exists and been existing for years to create 3D point clouds, and that can be very, very powerful, because disaster damage at the end of the day is not a 2D phenomenon, it's a 3D phenomenon. And being able to assess disaster damage in 3D is exactly exactly what you want to be able to do as a humanitarian expert. And it's important to note that every pixel here is geo-referenced. This is ortho-rectified, and that's really, really key for humanitarian applications as well. It's not just telling the UN there's a damaged building somewhere in this town, but actually giving them the GPS coordinates. And it doesn't need to be static, right? You can actually do these fly-through models and decide where you want to survey, where you want to fly through, and so on. So one of the next things we're looking to do is bring these 3D models directly into micromappers and crowdsource the analysis of 3D models. Now, I'd love to find out from you, is there an equivalent to do this in your fields of expertise where you would want to do a 3D model, whether it's crowdsourced or not, and analyze these? Eventually, and we're already starting to talk with a number of companies in LA and in New York, is can we bring these 3D models directly into a virtual reality environment and have digital volunteers analyze these 3D models directly within a virtual reality environment. Now, of course, this is not something we're going to be doing in Nepal tomorrow, although there's a very active robotics group at Kathmandu University. So what we decided to do, and this was really important as well to our code of conduct, is given that many of our local partners did not have easy access to laptops, tablets, and smartphones, is we decided to print out our maps on these large waterproof rollable banners that are far more durable in the field if it rains during the monsoon seasons. And we brought these maps right back to the local community and carried out what's called community mapping or public participatory GIS, inviting the community to actually hack the map by adding their local knowledge directly to the map, by creating a rich social intelligence layer to add context to the map, identifying priority areas for rebuilding and reconstruction. And the response was just outstanding. For over half a day, we had dozens and dozens and dozens of members of the community interacting with the map, adding data to the map, local knowledge that only they have, and catalyzing conversations on priorities, how to best rebuild, what to focus on, what strategies, and so on. And because we were not doing this over just a little laptop where you'd only have men basically around you, because we were doing this in a public space openly, all members of the community were able to participate and engage in the conversations. And so for the first time ever, the community of Panga was working off the one and the same data set to inform their discussions, to inform their rebuilding efforts. Not something that was subjective or anecdotal or hearsay, but actual concrete empirical data that they could interact with. And so it was a really, really big win. So that's my story. This is part of Kathmandu Flying Labs. What we're doing with UAViators is we're working with a number of local partners all around the world to co-create and co-host flying labs. We're already starting in Nepal, so we're going back in March to do more training, this time with fixed-wing UAVs. And also there's a lot of interest with hospitals and health clinics to use UAVs for payload delivery of medicines, vaccines, diagnostic samples, and so on. So we'll be hopefully in March, second half of March, for 2 weeks, again, training our local partners and carrying out these missions. And we're in talks with literally dozens of other countries, partners in dozens of other countries, from Indonesia, Malawi, Liberia, Rwanda, Chile, Haiti, Philippines, Maldives, and others, to co-create flying labs there as well. And they're not limited to disaster response. They are to try and basically transfer the technology, transfer the skills, transfer the knowledge to apply aerial robotics in a wide range of sectors, fields of expertise, including your own. So if you're working in any of these other countries or you're interested in co-creating a flying lab, definitely let me know. I'd be very keen to collaborate with you. Thank you very much.
Thank you, Patrick, very much. And we do have time for questions.
Hey, thanks. Really great presentation. Steve Adler from IBM. I was just curious, have you thought about using algorithms to identify the collapsed buildings when you're doing the flyovers? Because you could dramatically cut the amount of time it takes to analyze the images. You could even do it in real time, because it occurs to me, looking at your images, there's clearly a visible difference between a damaged building, in many cases, probably not all.
No, you're right.
There's probably some types of damage that you can't identify with algorithms, but you could probably get maybe 80-20. Crowdsourcing to do the other 20. Have you thought about that?
Yeah, no, it's a very good point. Absolutely. And it's part of the rationale behind the collaboration with EPFL is it's as important to detect when an image does not have a shelter or a building or a house, because, and volunteers have complained a little bit because most of the time they'll see pictures with nothing, and then they get kind of bored and then they don't engage anymore. So yes, one of the ways that we're trying to approach this problem is using these machine learning algorithms, these classifiers, to try and remove the noise so that only only the signals are sent to the volunteers who then assess the level of disaster damage. So absolutely, it has to move towards a combination of crowdsourcing or human computing and machine learning. And hopefully the holy grail would be in real time. We've done this with text-based information, but what would be really great is as volunteers are tracing these images, the machine learns in real time and then can automatically parse the rest of the images. So Drone Deploy is doing some great work there. They have what's called a algorithm store where they've got different classifiers for different features relevant for agriculture, environmental sciences, humanitarian, and so on. So it's a big area for computer vision, and we're just at the tip of the iceberg. So it has to happen. We're just scraping the surface of that. Yeah.
Hi, Jane Weingrove from JPL. Curious about the use of the DJI Phantom. Is it a matter of just a time lag, or given you're trying to train locals, why not use open source hardware?
Oh, very good. Good question. So we're actually really committed to open source as well. We're collaborating with UNICEF in Malawi and trying to bring open source solutions there. The issue is that so far, and I hopefully won't get in trouble with too many manufacturers, the open source solutions that I've seen are not as safe and reliable and robust for now. Because we don't want to just fly them for a week or two. These are platforms that need to be able to work around the clock as well as in different weather conditions and so on. But we are talking with a number of other groups in Silicon Valley who are more pro open source about using their platforms in Malawi. The first step with these flying labs is to transfer existing robust, reliable, safe technology to demonstrate the added value. And the second phase of that is more of a maker-faire hackerspace where we'll work with the robotics department and the engineering department at Kathmandu University to start then building our own UAVs from open source solutions and so on. But the way we did it, the reason we did it that way, by the way, is not because we thought it was the best way. It's because it's exactly what we were asked to do by our local partners. They said, no, before we can even go to phase 2, which was what we wanted to do first, we need to demonstrate the added value of aerial robotics in Nepal and get the CAA on board and get the government on board, and then we'll start designing our own. So that was what they preferred to do in that case. But I'd love to talk if you have other suggestions on what open source solutions that may not be on our radar. I'd really love to know. Thank you.
Hi, I'm curious about the experience with working with the locals in Nepal, where they were mapping out on the printed maps that you had of what the different buildings and infrastructure were. Was there a learning curve for them with working with aerial photographs? Because, I mean, we're used to looking at maps on, Google Maps or whatever, but if they don't have a lot of laptops, tablets, or things like that, they haven't necessarily been looking at aerial photographs, and things look very different from top down than they do when you're on the ground.
That's very true, and that was one of the big learnings I had in Liberia a few years ago, working with satellite imaygery and local communities. There's nothing intuitive about looking at aerial photographs that you would recognize your house immediately. I think we're all we may be more interactive with that, so it's more intuitive for us, but really there's nothing intuitive at the heart of it. That's why we do the trainings, both classroom-based trainings at Kathmandu University for the faculty, for the students and NGO representatives and governments, and then when we went to the field in Panga, it was a CDMC that took the lead in doing the community mapping and explaining to the community members how to recognize where their house was and go through that learning process. But that was not our comparative advantage to do. That was really the CDMC, who obviously knew the language, knew the community, knew the culture, knew how to explain this far better than we could ever have explained it ourselves. So they took the front seat, behind the wheel, and drove that whole process in helping to educate the community. Now, the local community in Panga is not new to community mapping. They've done this already with the CDMC, but not with aerial photographs. So this part was new. I will ask you a question when we go back in March, get some more feedback. There's a bunch of questions that I wish I had asked, and it's so much easier because a lot of our local partners are really just on a cell phone. They're not going to be an email and so on. So when I go back, I'm going to spend some time in Panga and just try and get some more feedback on how the map was used, the conversations that happened after we left and so on. That was a good question. And it's important to note that nothing about overhead imagery is intuitive inherently.
Okay, we've got time for one more question.
Hi, you mentioned the size of data that are generated from the flight, and I was wondering if you can talk about the methods or the strategies for saving the data or the images.
So I don't. So the question was strategies on how to operate these platforms safely.
Oh, sorry. Strategies and methods to actually preserve these images and data for long term.
Yes, that's a really, really great question as well. So there are a couple platforms that may be of interest, but you might already know them. One is Mapbox. So in Vanuatu with the World Bank, we put all our orthorectified mosaics on Mapbox and made that publicly available, thanks to the government of Vanuatu, who agreed to put this under a Creative Commons license. So we were able to surface it and make it more public than we would otherwise have been able to. But increasingly, we're shifting towards a platform called Open Aerial Map for aerial imagery, and that's a fully open source platform. And the World Bank's been using it, and others have been using it. And it's really meant to be an open source repository for aerial imagery, so that we can share imagery and have the same standard format that we share this imagery in, which is obviously really key as well. So that is one way. And then Dropbox is very useful too. It doesn't have to be anything fancy. Of course, you can go fancy. S3 has some phenomenal platforms. In fact, we've been talking to them quite extensively over the past few months, and they're coming up with some fantastic solutions with aerial imagery for aerial videos and so on, really high-end sophisticated stuff. So that's obviously an option as well.
Right. Let's thank Patrick again.
Thank you.
And I'm now going to hand it over to Dave Jones of StormCenter.
Thanks, Peter. It's my pleasure to introduce the next speaker, who also not only works at StormCenter, but is the Chief Technology Officer. Rafael has been a tremendous contributor to technology development at StormCenter, and has been the principal investigator on small business innovation research contract that we were awarded through NASA. And that took us through a phase 1, and then a phase 2, and a phase 3 contract, which has now positioned StormCenter to work with any federal agency on a sole source basis. So contracting can happen really quickly. It's been terrific. Rafael's contributions to geospatial information, I think it's timed out perfectly with the entire morning session. The focus is how to access and share geospatial information in real time in a collaborative environment, even independent of what platform you're using to visualize your data from a mapping standpoint. So without further ado, I'd like to address the newest U.S. citizen in the country. Rafael will be sworn in on Friday, so we're really excited about that, and so is Rafael. So. And if you have any questions about U.S. history, now is the time to ask Rafael. So, Raph, take it away.
I just passed the exam yesterday, actually. Yesterday morning, I was in Baltimore. So that was kind of nerve-wracking, but it worked out good. Very excited, obviously. So, as Dave said, I put together a little drawing here right after I heard Kerstin talk, because she really got to the point there about where is the value in data, really, right? And I just kind of clumsily put together this, and just kind of like to allow everybody to understand where it is we operate, where we play. So, as we all know, there's this big data strategy, this transport of data from the source through storage, processing and analysis, and then the output. And we're all talking about different aspects of this. What I'm going to be talking to you today is what happens here in the output and beyond. How do you collaborate with that output, right? The visualization and collaboration component of it. Per our experience, what we've noticed in working with agencies like the National Weather Service and emergency managers across Maryland and Virginia is that a lot that's being done is almost like a proxy to collaboration. So just like we're doing right here, where we're screen sharing to others, that's kind of what's being used in general to be able to collaborate with data. And I'll be showing exactly what my point is right now. So as some of you may have already seen either in the past or yesterday when I was doing some presentations there just right here next door during the NOAA event, what we work at StormCenter and this technology, GeoCollaborate, what it does is it allows for commonality across common operating pictures. So, you know, this map viewer here, and I'm sure everybody is familiar with web map technologies. If somebody wants to talk about it a little bit later, please come up to me. But you know, basically a web map is an interactive map, just like this one that I have here, and it's in a website. So what used to be a license that you had to have on your computer to be able to view GIS data nowadays is available to anybody by just going to a website. And I'm going to show you how this is being used operationally across different agencies. Now, what you're looking at here is a little example of GeoCollaborate. This is just the web page. And as you might see, as I do changes on this web map on one side, these changes are reflected across all the web maps connected to it. So if I turn on layers on any of these web maps, they'll turn on any web maps that's connected to it in real time. It's kind of like replicating the state of the web map across all the followers. What we discovered, though, is that here's a good case scenario. In the first year where we were working on our phase 3 contract with the National Weather Service, this occurred in Baltimore. There was a train derailment and there was a pretty big explosion that created kind of like a pretty nasty cloud that was coming out from where this explosion had happened. And, you know, if you talked to emergency managers or, you know, to the Maryland Emergency Management Agency, they were able to pinpoint exactly where this explosion occurred. So, as we all know, the National Weather Service, in response to requests from emergency management across the state, will typically do their best to kind of like inform these emergency managers as to what's occurring now and what will occur with this event. One of the tools in the arsenal is the high split model. A high split model, I'm sure many of you are familiar with it, but basically what it is, it's a dispersion model. You throw contaminants into the air and which way are they going to go in the future? What's the forecast for that? To run these models, you actually have to be verified. You have to be part of the system. They will only let you run future models if you've been accredited. So National Weather Service forecasters, for example, can run it. You have to give them an input point. You have to kind of like tell them what kind of event it is, what kind of smoke or, you know, dangerous material it is. They'll input it into the system. They'll start the screen sharing presentation, just like we are doing right now with everybody who's collaborating with us over the web. And they'll talk about this event. They'll talk about how the concentrations might be in different areas right now, which areas are going to be affected over the next half hour, 1 hour. What is it that happens at the end of this presentation that the National Weather Service has just given emergency managers and public safety stakeholders across the state? This. No worries, everybody who's online, you're still connected. This is just a screen that I'm putting there. Nobody has been disconnected from this presentation, but this drives the point, right? So you get a briefing, you're being shown data. Now it's up to you to take decisions with that data, but this is what you're left with. And these are emergency managers, right? They're not data analysts. They're guys who have to take really fast decisions, you know. And how do they take their decisions? They use tools like this one. This here is called the Osprey Map Viewer. It's what public safety stakeholders in Maryland use for situational awareness. It's an interactive map as well. It's one where you actually have to log in to access because, as you might notice here on the side, in this sidebar is where I deployed all the, a couple of the menus of the layers that they have, but there's a ton of layers here. There's things from like road conditions to what traffic is out there. You can access the cameras on the highways through this. Very valuable tool for emergency managers. What's the status of our shelters? They can immediately see on the map if a shelter is open, closed, being repaired, whatever. Very good for situational awareness, especially for that audience, that specific audience. There's a lot of data behind this, right? Billions of, as was said before, billions of bytes all being put down to, just a few kilobytes so that anybody can access this on their computer and take a decision. Unfortunately, though, that data set that I was showing to you before from the National Weather Service is a data set that was spun off, created at the forecast office, and shown via screen sharing. Well, now, thanks to the work that we've been doing under our SBIR and with the National Weather Service and with NEMA, as you might notice there's an NWS GeoCollaborate button there. As you activate that, what you'll notice is that the data set that was not previously loaded on this web map now appears. And any changes that I might make to my viewer here, so if I continue zooming in or out or moving around and doing things or adding data layers, let's say, for example, just as an example, that I want to load some snow forecast. It's not going to snow, guys, as far as I know. I don't know, maybe it is. This is an archive to snow forecast, okay? But this is another example of a data product that comes directly from the Weather Forecast Office. This is actually an AWIPS export. So it's, as you can see, that weird shape that it has, it's actually the Forecast Office domain. It's all the counties that the Sterling Weather Forecast Office has under its domain, if you may. Now, this data layer, as before, now appears as well on the emergency managers web map so that they can continue doing their analysis. I'm going to disengage from GeoCollaborate on this web map. And not only do I regain control of my map and any layers that I might have in here that I'm interested in looking at, but I can now ask the layers that have been put into this web map, things like inquiring them, how many inches are going to fall there, zooming in, which areas are actually going to be affected by this, which areas are not. This is a quantum leap over what was before, which is that screen sharing presentation, right? Maybe at best some PowerPoint slides after the presentation, but not data. So, here is an example of the National Weather Service, a repository of data sets that they have. And now National Weather Service forecasters can actually go in here, kind of like look at what web services are available and add those in real time onto their web map viewer. This is also a huge advantage. You know, many of these map viewers, you require a developer maybe to be able to change the contents of it. What we've been able to create to allow the forecasters to update this data in real time are these tools where layers can be added into this. The type of layers that we're adding into them are standard industry ones, are ones that will look very well on any web map viewer, as you can see there. And the trick now is, what are we doing to improve this, right? Now, this is a little risky, but I'm going to give the opportunity for everybody to actually join my collaboration. So what I was doing right there on the computer, if you want to go to this address, rafael.geocollaborate.com, on any device. If you want to go on your cell phone or on a tablet or on a computer, We know we've been having some internet connectivity issues. If it doesn't load immediately, be patient. This technology is actually designed to survive intermittent or slow connectivity. And what you'll notice is if you follow these instructions, where you go to the site, you click on that follow button, and you turn GeoCollaborate on, you'll see there's an on-off switch, and it's easy to use both on computers or on your cell phones. You will engage and connect, get the data sets that I was just showing. And you know, what I'll do here also is I'll zoom in a little bit into one of the areas where I was looking before, and whomever's connected with me right now will actually be able to see those layers as I move around and do things with them. So I'm going to zoom in into Baltimore, which is where we were before. And anybody who's connected and turned on GeoCollaborate should be joining me and seeing this data set. You can disengage from GeoCollaborate. All right. You can disengage from GeoCollaborate to regain control over your map at any time. If I were to continue and load more data sets and everything, these data sets are being put in real time on your computers. Be patient if it's not loading immediately. That's the trick too, right? During this is reality, right? During emergencies, the network will actually not work that great. So, you know, even getting a few kilobytes through is not going to work. And the issue is that if you're using screen sharing, it's only going to work worse. So people who actually need to receive a briefing, and this has been reported by MEMA, not even in the worst type of conditions, up to 50% of the users that are on the call or that want to get on the call never see any visuals, either bandwidth issues or because they're driving to the emergency operations center. So, you know, half of the information that's being distributed is not being seen. And we all know visuals is everything, right? An emergency manager who now has to kind of like imagine where something has occurred or look at a PowerPoint slide of a screenshot that occurred 2 hours ago and things like that, that's not the way to do things, at least in our opinion. So I'm going to just touch a little bit on the work that we're doing with the ESIPs. As you might see here, Dave has been working very hard with the ESIP Disaster Lifecycle Cluster, and we have been able to initiate a couple of projects with the University of Alabama in Huntsville and JPL, and they have their viewers, and here's what's wonderful about them having our web maps. They're actually telling us which data sets they use frequently, and they're asking us, how can this have value for the end user? How should it be presented? How should the end user be able to access these data sets? So this is all the kind of things that we're able to do now thanks to this technology. We also recently have, with the All Hazards Consortium, and specifically under the Multi-State Fleet Response Working Group, also under the ESIP Disaster Lifecycle Cluster, we're going to be working with them, and these are real-world operational folks. This specifically here, this Multi-State Fleet Response Working Group, is all about being able to get people and materials to the right places when a disaster strikes. Example, Maryland after a hurricane. All PEPCO is going nuts, right? Half of the state is without power, many lines are down, trees have fallen everywhere. They need help. Other states send help to Maryland. Other utilities will send help to help out Maryland utilities. But guess what? They'll all get stalled at the Easy Pass toll booth. That's it. No response coming from, the north because of that. So these are the kind of events and kind of things that these guys specifically work on. What we're going to be working is how to better integrate the data that you have and Earth science data and the data that NASA and NOAA can deliver to these folks so that they can start sharing this data using these tools. So having asked everybody to kind of like play a little bit and log in, I know that we were running a little with a little less time before, so I'm going to be finishing off my presentation and opening it up to questions.
Thank you, Rafael. And we do have ample time for our questions. Come on, we could sort of do a denial of service attack on the site here. This is ESIP, remember?
And I did do my presentation in English. I was thinking about Spanish at first, but...
I want to know, did you use an Etch-a-Sketch in that first part of the talk?
Hi, Rafael. Thank you for the nice talk. This is Emily from JPL. I just want to actually part of a session later. It's called the Trusted Data for Disaster Life Cycle Applications. At 4 o'clock today, we'll actually get into a lot more details on these applications, that wonderful application you have just seen. We're actually going to be doing some demos and additional talks about it, so I hope you can join us.
Thank you.
In this demo, you showed the information coming from one source, but in disaster response, there might be additional people with authoritative data. How do you handle if there's information coming from more than one source?
Thank you. That's a really good question. So the system, the way it's developed, is actually to be able to retrieve the data from wherever the source is. I have this little extra slide, which is coming in really handy right now. The idea is that as a leader, this web map that's leading right here, as I add a data layer onto my web map, all the followers are able to get that same web map information from wherever the source is. So in a sense, we're data agnostic. What GeoCollaborate does, in the same way that web map services put web map data onto web maps, our service, what it does is it enables collaboration on web maps. So data agnostic, web map agnostic, as you might have seen before, that, and I can bring it up again actually, that Maryland Emergency Management web map that we brought up is not ours. This isn't a web map that we constructed or that we kind of like forced them to use. They already have a web map. And that's actually a very critical aspect of this. The folks that you're trying to reach with data already have applications. They're trained for those applications. They have credentials for those applications. They've spent a lot of money putting together these applications. And then when you're trying to show them data, you're saying, oh, go to WebEx or, go to this other map viewer. Well, that doesn't work that well. The best case scenario is to try to integrate the data into those web map viewers, regardless of where the data is coming from, so that the end user can still have access to all those web map layers that are important to them, like shelters, traffic, and combine them with whatever data layers they should be looking at for whatever might be occurring. Is it a disaster? Are you talking to them about long-term effects of climate change? They'll understand it much better if it's on their data dashboards. I hope that answers your question.
Hey, Rafael. First, I'd like to set a good example for others by introducing myself before I ask a question. I'm Ted Haberman from HDF. Second, I'd like to thank you for coming to our country. And let's see, I had another question. What role does metadata play in making this system work?
That's a really good question, too. So the users, the lead users, are the ones that are in charge of the data that's being delivered, right? Our system is compatible with whatever standard GIS formats are out there, including legends, including metadata. But we don't do that metadata. We don't do those legends. And what we have observed is that not only end users, not only the emergency managers at the state and local levels, but even the weather forecasters at the weather forecast offices need to be able to access metadata and understand what data sets are reliable, which ones are going to be there 24/7. Because the worst thing that can happen to a forecaster is to be giving a presentation where the governor of Maryland is on the line and for the data not to be there. when you're expecting it to be there, right? So there's those needs, but there's also the need, and here's where, metadata or metadata plus, if you may, comes in, where what you need is information on what events and what users can benefit from those data sets. So beyond, our typical lists of data, metadata, where you have the publisher and the date and the description and who you can call and things like that, there's also a need out there for, well, I'm an emergency manager and I'm in Maryland. And as we were yesterday at One Stop, Noah was talking about that idea of having a Netflix experience, right? Where once you log into the system just kind of like prompts you, well, you've seen this before, so you might like this. It's the same kind of idea. You're an emergency manager, you're in Maryland. Guess what? Here's this event that's occurring that you might be interested in looking at.
Rafael, question. Steve Adler, IBM. Patrick. Since Patrick is on the stage, I wanted to ask, Patrick, have you looked at this thing that they got from StormCenter? Nah. So the reason I ask is because, Rafael, you guys should be working together. I remember back in Hurricane Sandy that I lived through. I'm from Long Island. We had 3 weeks without power. We probably would have only had 2 weeks without power in the town that I lived in if guys like you had come with UAVs and done mapping of the damaged areas first, because it took forever for the Long Island Power Authority to figure out where all the downed trees were, where the destroyed transformers were, all that stuff. And that information, that physical information about damage, would be great to see mapped in stuff like that. Because what you guys are both at opposite ends of the sort of political spectrum, right? The volunteers who are out there capturing information using drones, and the policymakers who are sitting in their bunkers looking at fancy maps trying to figure out what's going on. And it'd be great if these two were connected. And I'm saying personally, I know we're going to get hit with another storm in New York. It's just a matter of time, especially with climate change. And I would like to know that my governor, and I certainly hope the governor of New Jersey would do this too, would be using tools like drones to map damaged areas, and that information would be available for policymakers to look at as they evaluate. Because one of the things that happened in Sandy was we didn't just have one storm, we had two. The first one came in and knocked everything out, and then we had an ice storm in which we had this heavy snow, which did more damage. And because we didn't have an understanding of where the sectors were that were still fully damaged, people couldn't map that out. So I would encourage you guys to figure out how to work together.
And I think now that I'm becoming a citizen, I can operate the UAV. Well, maybe not then.
Patrick, did you want to come in?
We will exchange. Done.
It's the dating experience that is ESIP, right? A little bit too publicly. Usually this happens in a quieter setting. More questions? Comments? Thoughts?
Yeah, the first briefing, I'm Walt Baskin, ASDC. You've been operating in third world countries where they don't have the infrastructure and the restrictions, very, very heavy restrictions that are placed. Are you doing anything in the US now, or is it because it's very restrictive and there are other agencies that got it and are going to fight for that control of the airspace? Or have you run across that at all?
That's a really great question. So my work over the past 10, 15 years has always been international humanitarian relief operations. So I've not done work in disaster response here, but you might have noted the American Red Cross is on our advisory board, and they've asked us to provide them with hands-on UAV. We provide hands-on professional UAV training for humanitarian organizations. We've done this all over the world. They're interested in getting trained themselves. And I think with the FAA moving forward, there's been more openness to the use of UAVs. It's still a problem with commercial applications, but that's getting better. I know that we're working with a university partner to put some trainings together for FEMA to use UAVs and Civil Aviation Patrol, CAP, I think it is. So it's moving, but my work is really not focused. If you talk to Lindsay and her team in Vermont, they've done some phenomenal work. They're really, really experienced in using a fixed wing like the EBs for disaster response, crisis response in the US. So they're one of the leading teams that I would invite you to connect with. But let me just add that unfortunately, the regulations are not getting any easier, internationally as well. In the Philippines, in Nepal, everything is getting harder. And this is problematic for many reasons, especially on the humanitarian side, when these technologies can actually make a very real difference. But the problem is that there's a complete vacuum, this is my own opinion, within the international humanitarian community as far as leadership goes. There's no international humanitarian organizations like the UN or the ICRC, the Red Cross, that's willing to go to all these regulatory bodies and make a case for humanitarian applications and make a case for why we need separate regulations that apply to us, that are not have to do with commercial applications and so on, because we're not doing this for commercial reasons. We're doing this to save lives. But until the UN or other groups step up and actually demonstrate some leadership in this space, it's going to be problematic.
So I have a question. So just scratching your head. Yep. Okay. So Patrick, you saw the ease in which sort of map layers can be brought into this application. I'm curious. You said you have geo-rectified images. Are they easily integratable? Are they in the open formats?
I would imagine. I'm not an expert on data formats and so on, which is why I've become a fan of Open Aerial Map. They've set up from what I understand, an interoperable standard that we're all going to be following in the humanitarian space that can be used with other platforms and so on. So I believe on the metadata side and so on, there's interoperability there. And it's super important. That's a point I didn't make, but it was made here very well. It's not just about one data set. It's about the information stack. It's about having multiple layers that you overlay one on top of the other in order to have more enriched contextual information on what's happened on the ground. So we've been experimenting with, overlaying social media information, multimedia content from Instagram, satellite imagery, aerial imagery, and so on. That's what it's really all about, the kind of platforms that was just described here. It's not just about one data source on its own is not useful as far as I'm concerned. It really has to be integrated with others, or at least it's not as useful as it could be. So I'm a big fan of that as well.
Do you want to add anything, Rafael?
No, nothing to add. It's
all right.
Got the point.
All right, I'll entertain, especially Nancy.
Thank you, Nancy Hopelheinrich, Knowledge Motifs, California. I have a question for Rafael. It occurred to me as I was watching what you were able to do with this tool that it's wonderful for disaster managers, but it might also be wonderful for disaster creators. And so I wondered if you had any comments you could make about security issues that have come up as you've been working with different people, and or what kinds of issues, how that could be managed a little bit. Those kinds of security issues.
So this viewer here, for example, this Osprey viewer that the Maryland Emergency Management Agency uses is protected behind their system. So you need to have the proper credentials, and it's, a federated credentialing type system where if all the servers that are connected to it are talking the same language, if you may, then you can go from one to another. But our advantage in this project specifically is that the National Weather Service is using public data. So on their side, there's no limitations or anything. Now, the web maps and data can be also protected separately. So the web map itself might be completely locked down, where you can only access it if you have credentials. But then the data sets that are being loaded into it can be a mixture of public data sets, like the National Weather Service ones, and private ones, which might be giving specific information just to MEMA authorities. Now, the next level of protection is who can alter those data sets, right? And that's where being able to establish trust when receiving these data sets. So, knowing that you're looking at your trusted web map and that a trusted partner from the National Weather Service is loading a data set that they know where it's coming from just enhances the trust level, right? Versus a layer that, somebody might have pulled off of another website or something like that. So that's really where we focus on the aspect of collaboration, the idea that you can have a person put layers onto your map viewer, onto your web map, and even if that person isn't standing right next to you, you can trust that those layers are being put in because the system is handling all those trusted sources, if you may.
Okay, let's thank Rafael again and Patrick. And because, thank you to both very much. So, and because this is ESIP, Emily has already mentioned that there is a technical session on the disaster lifecycle cluster activity, which is in ESIP. And Lindsay is running a drone cluster session at Thursday at 2 p.m. So, direct sort of feed out from the things that you've heard here. If you want to find out some more, this is the place to go and learn some more. It's the end of the morning plenary. So from here, if you're not familiar, we have lunch. Lunch is out there somewhere. And
aren't you glad I finished early?
Yeah, he's hungry. And we're going to have, we're going to eat, and then we're going to have the awards part, and then there still is enough time to sort of socialize and mix before coming back to your technical parallel tracks at 2 p.m. And don't forget to come to the poster session today, because I believe that the Funding Friday awardees will be having some presents. At least you can track them down. They're meant to. I'm sure there's a lot of really good things in the posters, and the abstracts and titles are in the program booklet. And I think I have it on good authority that the total number of registrations at this ESIP meeting is 268. 273, which is the largest winter meeting that ESIP has ever had. That's cool. And so thank you very much. The last thing I want to do, some of you probably know that we're broadcasting live onto YouTube, and my wife, Erica Vale, is watching us from Italy, and she's been very entertained by the morning session, which I think is fantastic. All right, go to lunch, come back.